Now we introduce another parameter b inside the function. So we have r equals a cosine b theta and r equals a sine b theta. So what does that b do to the graph? How does that change the graph? So notice in rectangular form, when we make this 2 instead of just 1, instead of having one cycle in 2 pi units, now we have 2 complete cycles of the graph in 2 pi units. So how is that going to look on a polar grid? So let's go ahead and plot some points. So I have the point here. Notice we're going out to 3, up and positive 3 and negative 3. I kind of wish I had made it 4 because it would have made nicer numbers. But let's go ahead and mark here. This is 3 on the graph. And we're also going to see a lot of points where we're at 1.5, where r is 1.5. So I'm going to mark where 1.5 is. This is 1.5. And I'm going to kind of mark this around the axis here so that I can easily spot that when I need it. Now, my first point is when I'm at 0, 2, or 0, 3, sorry. So that would be 3, 0 in polar form. Then I'm at pi over 6, 1.5. Okay, so pi over 6, 1.5 is going to be 1.5 pi over 6 in polar form. My next point here would be at pi over 4. That's halfway between pi over 6 and pi over 3 is pi over 4. Pi over 4 is 0. Well, pi over 4 is 0 is just going to be 0 pi over 4, so I'm right here. So I'm going to stop, kind of pause the video and label those so you'll know what I've done on the, actually I'll just do it really quickly. So this is 0, 3, this is pi over 6, 1.5, and this is pi over 4, 0. And I've plotted those on polar form. Okay, so now we're down to negative values. So now I'm at pi over 3, negative 1.5. Okay, so pi over 3 is right here, but negative 1.5 is going to swing me back down here into quadrant 3. So that's right here. Then I end up with pi over 2, negative 3. So pi over 2, negative 3 is the same as 3 pi over 2, positive 3. So pi over 2, negative 3 is down here. Now we're back up to 2 pi over 3, negative 1.5. So 2 pi over 3, positive 1.5 would be here. 2 pi over 3, negative 1.5 would be back in quadrant 4 right here. So let's see what we've done so far. We've started at 0, we've kind of swung around here, gone back through 0, swung around here, made a loop, and come back to, I didn't actually put this on, but we're back to 0 then here. Now let's keep going. Now we're back up to 5 pi over 6, 1.5. And then we're up to pi 3. So let's do that. So 5 pi over 6, 1.5 is right here, and then pi 3 is right here. So remember, we're going 3 units out from the center in the direction of the angle pi. So if we took 3 and then rotated around a pi, we'd be right here. Back down again to 1.5 at 7, oops, I went down a little too far. So we're at 1.5 here at 7 pi over 6, 1.5. So 7 pi over 6, 1.5 would be right here. So, and then we get back down to 0, halfway when we're at, it actually doesn't really matter because we're going to go back to 0, whatever the angle is, but it's that would be at 5 pi over 4. So we're swinging around here, back to 0. Okay, now back to negative values. All right, so 4 pi over 3, negative 1.5. 3.2, negative 3. So we're looking at these 3 angles. This is negative 1.5. So 4 pi over 3, negative 1.5, ends up back in quadrant 1. 3 pi over 2, negative 3, ends up back up here. 5 pi over 3, negative 1.5, ends up back in quadrant 2. So we've made another loop. There we go. And then we're going to finish up, got to 0. Now we're going to finish up with pi over 6, positive 1.5, and 2 pi 3. So pi over 6, or sorry, 11 pi over 6, 1.5 would be right here, and then we end up back at where we started from. So we have what's called a polar rose. It has 4 petals. We start here at 0. We curved around like this and ended up back where we started from. Notice that the 4 petals correspond to the loops that are above and below the x-axis. If you imagine squishing the x-axis in from both sides until it formed a single point, which is what we have here, everything that's on the x-axis in the rectangular form is right at the center, at the pole in the polar form. So if we imagine kind of squishing the sides of this graph in so that all these points right here on the x-axis landed on top of each other, then we would just have these loops here, 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 and that's where we're getting these loops from. Almost imagine circling it, squishing it together, and seeing these loops kind of form a circle. Now if we look at the next graph, we see 1, 2, 3, 4, 5, 6 upper maximum and minimum points in between 0 and 2 pi. So we would anticipate then a 6 petaled rose. So let's go ahead. We notice that all of the tips of the petal are at these high points and low points. So here's the point 3, 0. Here's the point -3 pi over 2. Here's the point 3 pi. Here's the point -3, 3 pi over 2. So all we really need is these high and low points that we got from here and here and here, and then this last one, which was 3 pi over 2, -3, and here, to correspond with those end of the petals, and then we just go back to the middle each time. So we can do that here, just kind of shortcut our process. So here's the point 0, 2. So we start at 2, 0. Here's the point pi over 3, -2. So we go to pi over 3 and then go opposite direction, -2. That would be down here. Then we're up to 2 pi over 3, +2. So 2 pi over 3, +2 is over here. Now we're at pi -2. Well, pi -2 ends up back here where we started from. So this point is actually repeating right there. Then we go to 4 pi over 3, +2. Well, 4 pi over 3, +2 is this one. That's the one we have already done. It's right here. Then we go back down to 5 pi over 3, -2. Well, 5 pi over 3, -2 is back over here at 2 pi over 3, +2. So it turns out we don't have 6 petals after all. We have 3 petals, and they just repeat. So we go around once, and then we go around a second time. So the second time we go around would be starting at pi. We go around a second time. So we have our, at pi over 2, that's when we started to repeat. So we got the entire rows with the 3 petals by the time we got to pi over 2. So we'd like to be able to graph these things without plotting a bunch of points. We'd like to be able to do it just kind of by knowing some characteristics of the equation. So what we want to do is think about the equations that we have. R equals A cosine of B theta, and R equals A sine of B theta. And think about, well, actually we haven't done the sine one yet. We'll just look at this one. And how do we know how long the petals are, where the petals are located, and so forth? So what we notice here, this tells us the length of the petals, the number on the outside, the amplitude of the rectangular graph. The position of the petals, notice, are the maximum points, and I actually should say the maximum or the minimum points on the rectangular graph equals the tips of the petals in polar form. Kind of petals here, petals in polar form. And this A corresponds to the amplitude in rectangular form. So the length of the petal is the amplitude. Now, the other thing we'd like to look about is how do we tell how many petals? So when we had 3 cosine 2 theta, we had 4 petals. When we had 2 cosine 3 theta, we had 3 petals. So we're going to graph some extra ones and see how do we see how many petals that we actually have. So if we go to Desmos, I've graphed 3 cosine of 2 theta. I want to give you a couple tips for graphing on Desmos. First of all, if you go to this little wrench here, the graph settings, you can switch from grid XY to polar form. So you have this nice polar grid to look at. You can zoom in or zoom out as you need to see the size of the graph that you're looking for. To type in theta, it's real easy just to type in theta and then it turns into theta, which is really nice. You could also find it down here, but this is easier. So here's 2 cosine of 3 theta. Let's just leave, we already know that this number tells me how long the petals are, so let's just change this number. So here's 3 theta. So notice when we had 2 theta, we had 4 petals. When we have 3 theta, we have 3 petals. What happens when we have 4 theta? Oh, we have 8 petals. When we have 5 theta, 5 petals. 6 theta, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 petals. When we have 7, just 7. So it turns out that it depends on whether B is odd or even. So if B is even, the number B is even, the number of petals equals 2B. If B is odd, the number of petals equals B. Okay, so that's how we can tell how many petals. And where is one petal always located on every cosine polar rows? So if we look here, see if we can see which petal never moves. They get skinnier and wider, but which one never moves? Okay, so let's look at this. We always have a petal that's at 0 because the cosine graph, if we look at just the rectangular form, y equals 3 cosine of 3 theta, or 3x here, okay? Notice 0, 3 is a point on that graph, so this is going to have a point at 3, 0 in the polar form. So we always start up high at 0 degrees on our rectangular graph. And by the way, if you just click on the circle, you can turn off a graph and turn it back on, which is really handy. So we're always going to have a petal at 0, first petal at 0 degrees or radians, whichever you happen to be in. So that means one petal is always over here, going to the right. Now let's see what happens if we make a polar rows with an odd number of petals if we make A less than 0 or B less than 0. So let's look at our Desmos. So we've got this right here. If we make A less than 0, make this negative. Let's take that away. backspace, and then let's make it negative again. Notice that every petal flips 180 degrees. It goes the opposite direction because now all my positive R's become negative and all my negative R's become positive. So whatever R used to be, it's now going in the opposite direction as it was. At whatever petal direction the petal was facing, it's going in the opposite direction. Now let's see what happens if we make this number negative. Turns out nothing changes at all. And that's because if we think of a cosine graph, we look at our cosine graph, if we do a positive angle or a negative angle, okay, think of what a cosine graph looks like. If we extend it on both sides of the y-axis, the positive value for x and the negative value for x gives me the same value for y. So it doesn't change my y value or my r value if I make the angle negative. Okay, actually that little illustration goes over here. Okay, the first illustration was that if a is less than 0, that changes every petal 180 degrees. Okay, so if I start out with r equals 3 cosine of 3 theta, and I have a petal here and a petal here and a petal here, then if I have r equals negative 3 cosine 3 theta, then now I have a petal here and here and here. So this petal changed to here, this petal changed to here, this petal changed to here. Okay, so now we're going the opposite direction. Now, when b is less than 0, no change. It's because cosine is an even function. Cosine of negative x equals cosine of x, or cosine of negative b theta is equal to cosine of b theta. So there's no change if we just make b negative. Okay, in the second part of the polar rows video, then we're going to look at sine graphs. And sines are very similar to cosines, but they just have one little extra difficulty that the cosine graphs don't have.